Friends, as many of you may have read recently in the news, that Nepal and China have jointly declared the new height of Mount Everest to be 8,848.86 meters. That is precisely 86 centimeter more than the previous height of 8,848 meter. But we are not here today to talk about how or why a mountain's height changes. Rather, what we want to talk about, friends, is how do we measure a mountain? That's our topic for today. Now, how does one do this? One obviously can't climb up a mountain with measuring tape, right? I mean, that's not possible. One does it through something called as indirect measurements. We'll find out how this works. But firstly, a little bit of history. One of the great surveying projects of British India was the Great Trigonometric Survey of India, carried out in the early 19th century, that is around 1830 to 1850. As part of this survey, two of the largest theodolites ever built were used. Now, what is a theodolite, friends? As you would know, in any trigonometric problem, we need at least one angle and one side of a right angle triangle in order to determine all the other angles and all the other sides. If you have one angle, let's say theta in this case, and you have any one side, let's say the height or the base or the hypotenuse, you can get all the other sides. Now, what a theodolite, I'll just write that. What a theodolite does is, it helps us with an angle. It's a kind of a rotating telescope which is mounted on a surveying instrument, like a platform. The British used 6 of these to survey and measure Mount Everest, and these were located at a distance of 160 kilometers away from Everest. It was a young Indian mathematician, actually, Radhnath Sikdar, who actually discovered Everest one morning in 1852, and he burst into the room of the Surveyor General, Sir Andrew Waugh of India at that time, and said, "Sir, I have discovered the tallest mountain in the world." According to Radhnath, who was a mathematician hailing from Calcutta, the height of Mount Everest was 8,840 meters, which is amazing because that's just 8 meters short of the actual height which we consider today. And remember, friends, this was in 1852, that is about 170 years back. Or rather, the history of... Okay, friends, so that was a fascinating history about the height of Mount Everest. But we still don't know how the height was found. All right? Let's come back to our trigonometric problem. We'll have to use a few basic concepts of trigonometry over here, which I will just explain shortly. Let's say this is any figure. Let's say it's a building. Okay? Or let's take an example of Qutub Minar. Let's say this is, something like that. It's Qutub Minar, right? And we want to find the height of Qutub Minar. Now, let's say I stand over here at a position about, let's say 100 meters away from Qutub Minar, right? And I use my theodolite to look up at the top of the Qutub Minar to get that angle. And I figure out that this angle is, let's say, 30 degrees. Okay. Now, students, this length from the base of this figure to here can be sort of calculated roughly. The point being, if I start from this end of Qutub Minar, I would be missing out on a certain portion, but that can be estimated because you can sort of figure out the width of Qutub Minar by even actual measurement. You could, in this case, you could actually take a tape and measure it. And once you get the width, you can just cut it into half, divide it by 2, and you can add it over here so that you get an accurate width from the base of the figure to the point where you're standing, because the base lies inside the figure. You have to start from that point which is inside the figure. Okay. And having done this, you can you apply the concept of tangent, which is called tan 30, tan of an angle, is the opposite by the base. So let's say the Qutub Minar height is h, we don't know it. This would be h by 100. And tan 30 or tan of any angle for that matter, it's a known value. It's a known value. You have trigonometric tables. It doesn't matter on the size of the triangle. It can be a big triangle or small triangle. As long as it's forming an angle of 30 degrees, the value of tan will be the same. So tan 30 is known to be 1 by root 3. So we get 1 by root 3 is equal to h by 100, and h is basically equal to 100 by root 3 is our h. Okay, and this can be calculated. This can be calculated using a calculator, and you can get your answer. You would know root 3 is about 0.57, so it will come to let's say around 40 meters, or you'll get an answer. You'll get an answer for your height of Qutub Minar. Right? However, students, when we come to a mountain, for example Mount Everest, the problem is a little more complicated. We'll understand this through the fact of a diagram, but I'm sure you all would figure this out on your own. That in a mountain, right, if I'm standing, let's say, at some point, and I make two lines, one line going to the base of the mountain, one line going to the top of the mountain, to form a sort of triangle. Okay, let's say I know this is 30 degrees. This problem is solved by the theodolite because that tells us the angle, no problem. And let's say I even know I'm standing at a distance of say 100 kilometers from the end of the mountain. But how do I know how far I am from the base of the mountain, which lies inside the mountain? It's a very complicated situation because it's geographical features. There are other mountains and stuff like that. It's not standing alone that you can measure it or estimate. In any case, it is very difficult to get this idea because it's the vastness of the subject which you're trying to measure. This problem was solved very brilliantly and very easily. It's very simple. In your 10th standard mathematics notebooks, you will find problems of this type by a German scientist, by a German mathematician, who gave the idea of taking 2 points of observation. All right. So let's say I extend the base of the mountain here, and I install theodolites at 2 points, A and B. All right. From both the points, I can measure the angle of the top of the mountain. That's not a very big problem. So let's draw one small triangle here. All right. And we can get the measurement of the angle. Let's say this angle is 30 degree and this angle is, let's say, for example, 60 degree. Okay. Remember, students, in trigonometry, we always need a right angle triangle. At least one angle should be 90 degrees. All right. So let's call this point as L and let's call this point as M. You will observe here two right angle triangles are forming. One is triangle ALM and one is triangle BLM. Right? There are two right triangles forming. The line LM, which is this sort of a 90 degree I've dropped, is a sort of imaginary line. We don't know what is its height and so on and so forth, but we sort of know that there would be a line, there must be a line which is connecting the top of the mountain to the ground in a perpendicular manner, 90 degrees. All right, 90 degrees. So this angle here, students, is a 90 degrees. I represent like this. Now, in this situation, there are two unknowns, essentially. One is, of course, the height of the mountain, the vertical height. So that is just your LM. I'll call it H for short. The other is this length, BM. We really don't know this length. It's the same problem because we don't know the base of the mountain, right? So I'll call this as X. Now, students, the point is we have two unknowns. But the beautiful part about mathematics is even with two unknowns, you can solve it if you can create two equations. Why you need two equations? If I have one unknown, I can solve it using one equation. For example, if I say 4x equals to 16, all of you can give the answer for this. You will say x is equal to 4. I solved it easy because there was only one unknown and one equation is enough. But when there are two unknowns, you need two equations to solve. This is known as simultaneous equations. Let's see. Let's take this example to better understand how we would go about in this case. Let me look at triangle ALM first. The angle here is 30 degrees. So I will here use tan of 30 degree, right, is equal to LM over AM, right? triangle ALM. Alright, let me just make a little bit of space here. Yeah. Now let's substitute values. Tan 30 is known to be the value of 0.57. LM is H. Now AM, students, you will observe, is the sum of two parts. It is basically AB plus BM. Right? You agree, follow up to this point? You all agree? Okay. Okay. If there are any doubts you have, please put it in the comment section. I'll explain this part again. All right. So we have 0.57 is equal to H by, now AB is the distance between the two theodolites. This can be known. This is up to us. We can put the theodolite wherever we want. So let's say the mathematician chose to put the theodolites at a gap of 100 kilometer. For an example, let's say chose to put it at a gap of 100 kilometer. All right. Therefore, your AM, which is this total length, students, over here, is basically 100 plus X. Because your AB is 100, that is AB is the distance between the theodolites, and BM is X, which is the base of the mountain to the closer point of the mountain, that is B. Okay. We will not be able to solve it because there are two unknowns, but we got an equation. So I'll just call this equation number 1. Right? We can solve it a little further. Let me cross multiply. So if I cross multiply and take it here, I would get 57 plus 0.57x is equal to H. We got one equation. Okay. Let's look at the second equation which we can get, which we will use triangle BLM. So I'll try that now. Okay. Now in triangle BLM, you'll notice the angle has changed. Would the angle increase or decrease? What do you feel? Yes, students, the angle will increase. As you are going closer to the object, you have to look up even more steeply to see the object. So we just take an assumption. Let's say it is 60 degrees, the angle now. In triangle BLM, I would take tan of 60 degrees. And tan of 60 degrees is what? It is the height by the base. So tan of 60 degrees. The height, we are calling it H. We have sort of assigned it. These are called variables. We assign it a value just to, for convenience. So H is the height and X is the BM, base, from the base of the mountain to the closer point B. Okay. Tan 60 is also a known value. It is 1.73, root 3 basically, is equal to H by X. And if I cross multiply this X, I get 1.73 into X is equal to H. I have two equations, students. Okay, I'll repeat the equations for you. Equation number 1, 57 plus 0.57x is equal to H. 1.73 into x is equal to H. What do you observe here? Both the left hand sides are equal to H. So we can equate this 1.73x is also H, and this 57 plus 0.57x is also H. So all I do is, we do something like this. (57 plus 0.57x is equal to 1.73x. Now the beauty is you have reduced it to one single variable, x, and you can solve it. It's just a simple question of addition subtraction now, which we will do. So 57 is equal to 1.16x. X is equal to 57 divided by 1.16. All right, and this value, of course, you may need to use a calculator or long division. I've sort of done it before. I came prepared with that point. So it's around about 49. 49.13 is the value of x. So let's approximate it to 50. So x, students, is equal to 50. Now what have we found? Have we found the height of the mountain? No, not yet. We have found this x, which is the distance of the closer point from the further point. The closer point from the base of the mountain, which is a very big thing. This is what was causing all the trouble. This was the troublesome fact in the first place, that we don't know where the base of the mountain is, so we cannot measure it. We cannot access that point to measure it. But now we know it. We know that this is 50 kilometer. Okay. And once you know x, therefore you know that your total distance is 150 kilometer from the second point, but you don't even need that. You need any one triangle to solve it. Let's stick to triangle BLM itself. In triangle BLM, we will use tan once again. I will say tan 60 is equal to h by x. Okay, but now x is known and tan 60 is also known. It was always known, tan 60. So 1.73 is equal to h by 50 because you found x. And therefore, students, as a last step, we just cross multiply, or rather we multiply both sides into 50. Okay, I do into 50 into 50, and you get 50 into 1.73 is equal to h, and voila, you have the height of the mountain, which in this case would come around 86.5 kilometer. Of course, that's not the real height of Mount Everest. This is just an exaggeration, just to get the point across. Okay. So students, think about this. Use it. Try to walk around in your locality. Look at buildings. You don't have a theodolite, I know that. But just look at the building and say, okay, from here, how much angle is it making? Kitna angle ban raha hai? Then walk a little closer to the building. Estimate. Make it 30 degree. Walk a little closer to the building. Look at it out again. Now how much angle does it look like? Measure how much you walked and use the system, students. You will actually be able to figure out the height of a building or a mountain maybe.